Welcome everyone. I am Nora Abdelmageed along with Sirko Schindler, Friedrich Schiller University, Jena, Germany. In the following slides, I'm presenting JenTab, a toolkit for semantic table annotations. Let's getting started with semantic table annotation tasks. At first, CEA assigns a knowledge graph identifier to individual cells. Then CTA matches the entire column to a semantic type. Finally, CPA captures column-column relationship. The rest of the outlook is as follows: related work, proposed technique, then the used datasets and our evaluation, the results, and finally, conclusions and future work. We have grouped the related work into 3 categories: benchmarks for evaluation, JenTab challenge participants over the last 2 years, and other approaches which integrate machine learning. Unlike the existing methods, JenTab is a modular approach which uses only the publicly available knowledge graph data sources. In the following, I will explain our preprocessing, choosing CFS pattern, the used context, and the architecture. Preprocessing involves 3 tasks: generic fixing, including encoding fixes, data type prediction, which is limited to those types of Wikidata. Finally, type-based cleaning as a further cleaning step for dates and quantity types. CFS pattern has 3 stages as follows: create all possible candidates for the 3 tasks, filter the initial candidate set by using feedback from other tasks, select the most suitable candidate from the remaining ones. We use both of the publicly available lookup service and Sparkle endpoint for Wikidata as our primary data sources. We leverage 4 contexts to create and filter annotations. Cell context uses only the plain cell value to query the knowledge graph. Column context leverages the semantic column type as well. Row context is used to generate properties for the subject cell, or in the other way around. Row column context combines the previous 2. Here is an example using the cell context. Multiple candidates are expected to be here. We have 4 primary strategies to generate candidates for a cell, each of which captures a different part of the cell to query the knowledge graph. The last 2 columns here demonstrate an example for each method. Our secondary strategies are meant for autocorrection. The generic lookup uses Jaro-Winkler distance, and it's executed before the actual pipeline. The autocorrect uses the one-edit distance with on-demand execution. A black box execution leveraging the column context is also here. As you see, a more accurate candidate is renamed. Here is an alternative execution which uses the row context and outputs an accurate candidate as well. The following are the rest of the annotations modules. CTA collects the types for all retrieved cells, while the CPA do the same on the properties level. For literal properties, we support a fuzzy match technique that allows a margin. For example, we tolerate 10% of numbers. Our filter functions drop the highly unlikely candidates. CTA support removes the types with a support that is less than a certain threshold. The same idea applies in the CA candidates filtration by their properties. The final stage of our CFS pattern finds a solution for each task by selecting the most appropriate one. The highlighted method nominates our primary method per task, while others are backup strategies. They are executed if the primary method failed to solve the task. In the following, I will explain the CTA selection strategies. CTA by majority is applied for the leaves of the hierarchy of the types. The retrieved types are treated equally, and only vote affects the solution. CTA by LCS applies the least common subsumer algorithm for the entire hierarchy. The solution goes for the lowest node with the highest coverage or vote. Lastly, CTA bidirect parents flatten the leaves with one level up and applies a majority vote as well. The sequence of modules is represented by the figure on the right here. Our core pipeline is represented by the first group, where no selection is done at this phase. However, group 9 represents our backup strategies of selection or our last resort. In between is a combination among the three phases of the CFS pattern. JenTab is a distributed system with a central node for workload balance. The other components are developed in isolated services. Such architecture enables scalability and knowledge graph substitution. Our use dataset is the one provided by the JenTab Challenge 2020, which is a combination between an automatically generated dataset and a tough table dataset. It includes more than 130,000 tables as a total of a 4-round challenge. 11 encountered the challenges of the use dataset, which are missing data, spelling mistakes, ambiguity, missing spaces, inconsistent format, nested pieces of information in quantity field specifically, redundancy of columns, encoding issues, noisy data, missing values, some nulls, some empty strings and special characters, and the excessive length of tables. We stick our evaluation matrices to the same used by JenTab Challenge for comparison reasons. For CEA and CBA, we have used the standard precision and recall, while for CTA, the score pays attention to the predicted type position in the types hierarchy. This means a more general solution may have partial score, but not the best score. Our experiments include 3 modes to solve the CTA task. From left to right, the solution becomes more general. The B31 experiment selects the leaves from the hierarchy and applies a majority vote. 2 hops strategy includes 1 level up, while the multiple hops includes more levels as well. Our results for the individual components of the system are as follows. For the type prediction, we achieved a 99% accuracy with this confusion matrix. For the pre-computed lookup, we achieved a high coverage near 99% for the first 3 rounds and around 97% of the last round. Since we have various strategies in the CFS pattern phases, we have computed the effectiveness of these methods in terms of the audit statistics. The CEA creation strategies reflects the priorities we set to them. For the CEA selection strategies, where the string similarity is our dominant method, it managed to solve 38% more than the backup strategy. Here is the audit statistics for CTA, where the majority vote is the primary technique of B31. For 2 hops at CTA selection, the least common subsumer is used as a dominant method. In this case, there is a less reliance on the backup strategies compared with the previous one. Here is our scores compared to JenTab 2020 top participants. JenTab is among the top 5 systems at CEA and CTA tasks, while it's among the top 3 systems at CBA task, where it doesn't use any offline DAMs or generic search engines. For the tough table dataset, and among our settings, unlike the automatically generated dataset, 2 hops mode achieved the best results. Due to the high level of ambiguity, JenTab has a limited performance on this dataset in general. For the multiple hops mode, it has the lowest scores due to its general solutions. A general solution could be correct, but not the best option, yet a lower score. The time analysis given a scoped execution here, for example, We set 1 hour to solve a table. Let's the overall running time converges faster. We have managed to reduce a 50% of the required time for the 4th round. In summary, I have introduced our JenTab toolkit for semantic table annotations, which is publicly available in the link below, in addition of 3 experiments for solving CTA with a detailed analysis. Our future plan considers optimizing certain components that require substantial resources, and investigating more technical reasons behind the limited performance of JenTab on tough table datasets. Last but not least, we would like to thank the following people, and thank you all for your attention.